Hello everyone. Welcome back to our mathematical journey through conic sections. Now let's start with something simple. Ever tried drawing a perfect circle by hand? You probably started okay, but somewhere it became an egg, right? Don't worry, we've all been there. But what exactly makes a circle perfect? Why does nature love this shape? From ripples in water, to wheels, to the moon's orbit. Today, we'll discover the math behind this most symmetrical of all curves, the circle. Imagine you have a fixed point, let's call it O, the center, and every point around it is exactly the same distance away. That distance is called the radius, represented by r. So, mathematically speaking, a circle is the set of all points that are equidistant from a fixed point O in a plane. If you double the radius, that's your diameter, or d equals to r. And the line joining any 2 points on the circle, that's called a chord. The curved edge between those 2 points is the arc. See, circles are everywhere. The wheel of your bike, the pizza you eat, or even the rings inside a tree trunk. Now, let's bring in coordinates, our trusty x and y axis. Suppose the center of the circle is at the origin, that's the point 0, 0, and the radius is r. If we pick any point P with coordinates x, y on the circle, the distance from O to P must always be r. So, using the distance formula, we can write OP squared equals x minus 0 squared plus y minus 0 squared. Simplifying that, we get x squared plus y squared equals r squared. Say it again slowly. X squared plus y squared equals r squared. That's our standard equation of a circle with center at the origin and radius r. And if you're a vector fan, you can express it this way. Magnitude of vector r squared equals r squared, or simply vector r dot vector r equals r squared. Isn't that beautiful? One elegant equation. X squared plus y squared equals r squared. That captures the entire circle in just one line. But what if the circle isn't sitting nicely at the origin? Let's say its center moves to a new point C with coordinates h, k, while keeping the same radius r for any point P, x, y on the circle. The distance from C to P must still be r. So, by the distance formula, we can write x minus h squared plus y minus k squared equals r squared. That's our standard equation of a circle with center h, k, and radius r. Now, let's expand this equation step by step. When we open the brackets, it becomes x squared plus y squared minus 2hx minus 2ky plus h squared plus k squared minus r squared equals 0. In general, we can write any circle in the form x squared plus y squared plus 2gx plus 2fy plus c equals 0. Here, the center of the circle is at minus g minus f, and the radius is equal to square root of bracket g squared plus f squared minus c bracket close. But remember, for the circle to be real, the term g squared plus f squared minus c must be greater than 0. Quick check. A real circle can never have a negative radius. If you ever get that, it means there's probably a sign mistake somewhere. So double check your algebra. Alright, before we jump deeper into equations, let's remember, geometry built the circle before algebra described it. So, a few golden circle rules every student must know. The perpendicular from the center to any chord bisects that chord, and also the arc it subtends. So, the perpendicular bisector of a chord always passes through the center. The angle in a semicircle is a right angle. This is Thales' theorem, one of the oldest results in geometry. Equal chords subtend equal angles at the center, and conversely, equal angles subtend equal chords. And the superstar property. The tangent to a circle at a point is perpendicular to the radius at that point. So next time you're standing next to a Ferris wheel, that ladder touching it? Yup, that's your tangent, always perpendicular to the radius. Let's now learn how to find the center and radius of a circle when the equation isn't given in standard form. Suppose you're given this equation. X squared plus y squared plus 2gx plus 2fy plus c equals 0. Looks a bit messy, right? But don't worry, we can clean it up easily using the classic trick, completing the square. Step 1. Group the terms. Put the x terms together and the y terms together. X squared plus 2gx and y squared plus 2fy. Step 2. Complete the square. For x squared plus 2gx equals x plus g squared minus g squared. For y squared plus 2fy equals y plus f squared minus f squared. Step 3. Substitute these back into the equation. We get x plus g squared plus y plus f squared equals g squared plus f squared minus c. And there we have it, a neat and tidy standard form of a circle. From this, we can easily identify the center and radius. The center is at minus g minus f. The radius is square root of bracket g squared plus f squared minus c bracket close. See, it's just like cleaning your room. Group the messy stuff, square things neatly, and suddenly everything looks organized again. Ready for a challenge? Let's now find the equation of a circle that passes through three non-collinear points, say P1 with coordinates x1, y1, P2 with coordinates x2, y2, and P3 with coordinates x3, y3. Step 1. Start with the general equation of a circle. X squared plus y squared plus 2gx plus 2fy plus c equals 0. Step 2. Substitute the coordinates of each point into this equation. You'll get three separate equations. x1 squared plus y1 squared plus 2gx plus 2fy plus c equals 0, x2 squared plus y2 squared plus 2gx plus 2fy plus c equals 0, x3 squared plus y3 squared plus 2gx3 plus 2fy3 plus c equals 0. Step 3. Eliminate c by subtracting the first equation from the next two. That gives you two linear equations in g and f. Solve those two equations simultaneously to find the values of g and f. Then, substitute g and f back into any of the three equations to find c. And that's it. You've got the equation of your circle. The center of the circle is minus g minus f, and the radius is square root of bracket g squared plus f squared minus c bracket close. Alright, let's wrap this up with some real-world context. Circles are more than just curves in your math book. They're everywhere, from the wheels that move cars, to the orbits of satellites, to the ripples spreading on water when you toss a stone. But in algebra and coordinate geometry, circles show up in locus problems, reflection physics, and even motion analysis. They quietly connect geometry and algebra in a way no other shape does. Now, before we finish, let's do a few quick sanity checks. Always take the center as minus g minus f, not g, f. Make sure that g squared plus f squared minus c is greater than 0. Otherwise, it's not a real circle. And finally, test your final equation with one known point on the circle to confirm it satisfies the equation. Let's quickly summarize what we've learned today. We began with the definition of a circle and derived the fundamental equation x squared plus y squared equals r squared. That's for a circle with center at the origin and radius r. Then we generalized it to x squared plus y squared plus 2gx plus 2fy plus c equals 0. Found how to complete the square to get the center and radius. And finally, we derived the equation of a circle passing through three non-collinear points. So yes, we really did come full circle with this topic, quite literally. It's amazing how one simple curve can tie together so many beautiful ideas. Geometry, algebra, distance, and symmetry, all in one neat package. In our next video, we'll continue our conic adventure and meet the ellipse, the stretched cousin of the circle, where distances twist and balance in a whole new way. Until then, keep your compass sharp and your curiosity even sharper.